Now let's solve the part 4 of this problem, which is finding the input impedance at 24 centimeters from the load. Something that we need to note here is that the distance that we are given is in centimeters and not in terms of lambda. And as we remember, all the distance that we plot in our Smith chart are in terms of the length, the wavelength. So we need to express the 24 centimeters in terms of our wavelength. However, from our givens, we were not given our wavelength, so we need to calculate the wavelength of our signal. Since we have a lossless air transmission line, we can use the equation lambda is equal to C over F. So let's calculate that. C will be the speed of light, and we have our frequency, which was a given of 3 GHz. This computation will give us 0.1 meter as our wavelength. Now that we have our wavelength, we can express our distance, which is in centimeters, in terms of the wavelength, and we will do that by dividing the distance by the wavelength. So let's do that. 24 centimeters divided by lambda. Let's transform this to meters. 0.24 meters divided by 0.1 meter, and that should give us 2.4. Since we are expressing our 24 centimeters in terms of the wavelength, that will be 2.4 lambda. And now we can express this distance in our Smith chart because it is in terms of the wavelength. So what does this mean? That means that we need to move from our load towards the generator by 2.4 lambda or 2.4 wavelengths towards the generator. So we need to do that. However, 2.4 wavelengths towards the generator, we know that in our Smith chart the maximum distance that we can move is 0.5 lambda. What happens after that is that another loop is measured. So in order to measure 2.4 lambda, that will be 2 lambda plus 0.4 lambda. These 2 lambda will represent, as I said, the maximum distance that we can draw in our Smith chart is 0.5 lambda. So these 2 lambda will represent 4 turns. So it will be coming from our generator, coming from our load towards the generator, it will be 1 turn, 2 turns, 3 and 4, and then we will move the 0.4. So it will, in other words, we just need to move 0.4 lambda from our load. The first step to move 0.4 lambda from the load is to calculate what is this distance until completing the whole Smith chart. So we need to do that. We have our position and we know that this position over here is 0.5 lambda. So we need to subtract 0.5 lambda minus 0.198 lambda. So let's do that. That should give us 0.302 lambda. So this means that going from our load, moving until here, we just move 0.302 lambda. However, we needed to move 0.4 lambda. So what we need to do is to find out how much we need to still keep moving in this direction. In order to do that, we will take the 0.4 lambda minus what we already moved until this position, and that will be 0.4 minus 0.302 lambda That should give us 0.098. Again, from our load, we move 0.4. We need to move 0.4 lambda. However, until here, we move 0.302, which is not what we needed to move. We needed to move 0.4. So 0.4 minus 0.302, we need to still move 0.098 in this direction towards the generator. So let's find out where is that 0.098. So we have in here 0.09, and we have here 0.1. So 0.98 will be 0.9, 0.09246, 0.098 will be this position. So we draw a line from the center of our Smith chart to that position. This line will determine the location of our input impedance at 24 centimeters from our load. Again, we did 4 turns and then the 0.4 lambda until reaching this position. Now we just need to read what is our input impedance, and that will be determined by the intersection of this line that we just draw and our SWR circle, and that intersection will be here. By having this point, we will follow this line until we see what is our imaginary impedance, which is 0.6, between 0.6 and 0.7. So it will be around 0.65. So we write that down. The imaginary part of our input impedance will be 0.65. Positive. It is positive because we are in the top part of our Smith chart. Now, in the same way that we follow this line to find the imaginary part of the input impedance, we follow this line to find the real part of our input impedance, and that line should be this one. If we follow that line until here, we see that the line intersects the real axis between 0.3 and 0.4. So we take a look at the smaller lines. So it will be 0.3, 0.32. Something that it is important is that, as I said at the beginning, all the impedances that we represent in the Smith chart are the normalized version of the impedance. So if we want to find the input impedance in ohms, we need to multiply what we got in here, which is the lowercase input impedance, times our characteristic impedance. So that will be 0.32 plus J 0.65 times our characteristic impedance, which was a given of 50 ohms. That should give us 16 plus 32.5 J ohms. Now we can use ohms because we are multiplying it with the characteristic impedance. That should be our final answer for this part.